16 plus 2 times 4 plus 0 plus 5. And we just calculate that out. That's 8, 16, 24 plus 5, 29. That's 29. So that's how we evaluate a polynomial. Like we've all done this before, and we've all done this a lot. So like, let's now think about like, is it possible for us to evaluate our polynomial at a point that we don't know? So let's pretend that we don't know x to the 1. We don't know this, but we don't need to know x to the 1 because we don't have an x to the 1 term here. So if we don't have that, do we really need to know x in order to be able to evaluate our polynomial? And the answer is no. We don't really need to know x to evaluate our polynomial. So like the next thing to think about is, well, is it possible to evaluate our polynomial at a secret point, at a point that like nobody knows? And it turns out that it is possible to do that. And basically what we do is we depend upon this like ceremony to generate the various powers of tau. I don't know if you heard about powers of tau. Well, powers of tau is like the phase 1 of the trusted setup ceremony. It's also like we're also running a powers of tau ceremony for IPI 4844, which is to provide like massive data availability on Ethereum. So that's our plan. And yeah, so that's the powers of tau. So let's have a look at this code here and see what it's doing. So wait, where did I think we should see this code, but I don't know. Where is that defined? Where is the powers of tau function defined? Yeah, it's imported from the library, but I thought it would be part of the tutorial. Okay, so let's just trust in the tutorial and say that, okay, well, we have this powers of tau thing that basically, just given a secret, calculates the different powers of G1. And G1 is going to be the secret point at which we're evaluating our polynomial. And it's really important that nobody knows what the secret point is, because if someone knows the secret point, they would be able to like create a polynomial that appears to be evaluated at the secret. They would be able to find like 2 polynomials that result in the same polynomial commitment. So let me slow down and talk about like the guarantees that we want to have from our polynomial commitment. The first guarantee that we want is we want it to be binding. We want it to be binding because like we want someone, when they commit to a polynomial, that they can only use that polynomial. They're not able to change and have another polynomial that they can use. Like we want it to be binding to sort of kind of like when someone commits to a polynomial, has a polynomial commitment, they're not able to change the polynomial underneath. If someone knew the secret point, they would be able to find multiple polynomials that had the same polynomial commitment. So that's why it's important that the secret point is secret. So yeah, this is our, let me try and bring up the actual powers of tau code because I want to go through that. It's in the library here somewhere, so let me check. Probably in polycommit. Here we go, powers of tau. Okay, cool. So like basically what we do is we take like a generator point. We take 2 generator points. We're talking about elliptic curves here, and like we didn't really introduce elliptic curves or describe how they work. So let's just build like a quick black box about elliptic curves. So basically the way that elliptic curves work is that it's like a one-way function. With an elliptic curve, you can multiply it by another number. You can go forward, but it's impossible to divide. It's impossible to go backwards. So whenever we're doing a multiplication, no one is able to go back in the other direction. So that's the idea of like multiplication. But that's the idea of elliptic curves, or it's one of the ideas. And this is used a lot in signature schemes. When a signature scheme, it relies upon the fact that you can multiply and go forward, but you can't go backwards. Okay, cool. So like, let's actually do our trusted setup. So let's calculate our powers of tau. So our powers of tau is very simple. It's basically just x to the 2. Is it x to the 2 or x to the 1? No, like it's x to the 0. Yeah, so it's some secret to the power. Let me see. Yeah, so it's okay. So it's g1 times secret. And then it's g1 times secret squared. And then it's g1 times secret cubed. So this is the like proving key. And what's our verification key? Our verification key is basically just like g2 and g2 times s. So this is our powers of tau. And basically we go through this and we calculate the various different powers of our secret. And like the important thing to notice here is that there's a correlation here, that this is like x, this is like x squared, this is like x cubed. And like the point that we're evaluating this at is our secret point. X is our secret. This is actually G1, X1. This should be 1. And that's 2, and that's 2. Yeah, so this is like our secret. Yeah, so like you see there's a correlation here. So, right, let's try and evaluate our polynomial at this point. Is it possible to do that? And the answer is that it is possible to do that. So basically, we take our polynomial here, and we say, okay, it's 5 plus 0 times x, 0 times g1s, plus 2 times g1s squared, comma, cubed, plus g1s cubed. Okay? And this is basically us evaluating our polynomial at a secret point. Nobody knows what s is. No one knows what s is. So like no one is able to like evaluate their polynomial at that point. They're not able to make their polynomial such that it evaluates to a certain value at that point, because it's a secret. And like when we do the powers of tau, this is basically like a trusted setup. And like the trust assumption is that someone forgets the secret, that like there's a single honest participant who forgot their secret or who deleted their secret successfully. Okay, so that's powers of tau. Let's go back to the notebook and let's read the code here and see what's happening. Okay, so basically the code here is saying, all right, here's a polynomial and here's a secret. For that secret, calculate enough powers of tau to evaluate that polynomial at the secret point. And that's basically all that we're doing here. The next step is like, okay, we're going to use polycommit. We're going to use, check the time. Sorry, let me slow down. Any questions here? This is very difficult stuff. This is not easy. And I'm not doing a good job explaining it.
You're doing great.
Thank you.
It's just the math is too complicated.
Yeah.
We just need to get the idea and we can do more research on it.
Yeah, I understand. It's not easy. It's not that. It's definitely not that, because we've already discussed a whole bunch of different, more difficult things earlier. It's just that like this one is more abstract, and like because of that, it's difficult to grasp. But when you get it, it's really actually a very simple idea. That like, let's abstract away. Let's use this tool. That's really important when we're doing research. Let's abstract away and try to find the simplest thing that we could understand, and see if there's pieces of it that we don't know. So like, let's say that like, okay, we want to have a commitment to a polynomial. We want to have a polynomial that's like, that we can describe in the smallest possible way. So let's say that we have like a friend that we trust. And let's say that we ask our friend to evaluate that polynomial at a secret point. And whenever they evaluate that polynomial at a secret point, they give us the result. They say, at the secret point, the value of this polynomial is 100. And they're our polynomial. In this case, they are our polynomial commitment. We're asking them to commit to a polynomial, and they're saying, okay, sure, here's the value. And like, it turns out that like, once we have someone that we trust to do that, we're able to have like binding commitments to polynomials, because like, because we trust our friend, and our friend has like this really big random number. It's really, really hard to find two polynomials that will evaluate at the same point, right? And let's investigate that a little bit, and let's see why. Okay, so let's draw a polynomial. Okay, so this is our polynomial. Let's say it's like this. Okay, and we tell our friend that this is our polynomial, and the polynomial is what? What is the polynomial that we're using here? 5x cubed plus 2x squared plus, no, it's 2x, right? Plus 1. This is our polynomial. So it's like y equals this. So this is our polynomial. We send it to our friend, and our friend creates a secret point, and they don't tell us. Let's say our friend creates a secret point, and this is their secret point here. They don't tell us that this is x equals 1. No, this is x equals 39, and then the actual value at x equals 39 is the value that they return to us. So this is what they do. They give us like a polynomial commitment, and they just give us y. And we say, okay, that's our polynomial commitment. And like, so why is it true that it's hard to find a collision here? Why is it true that it's hard to find two polynomials that evaluate to the same thing at the secret point? So like, the rough intuition is that like, there's many secret points. Like, we don't know what their secret point is. So if we just create another random polynomial, it would have to go through this point. If it goes through this point at x equals 32, then we would find a collision. But because we don't know that, when we're creating our polynomials, we never go through that point. We never go through here. So this is like, oh, cool. So like, another way to look at it is that like, a polynomial commitment is like a secret gate, right? And it's kind of betting that like, you'll never be able to find the secret point, right? If you're able to find the secret point and put your polynomial through the secret point, then you're find collision committed to. But like, because our friend won't tell us, it's really, really hard for us to make another polynomial that passes through this. Like, right? Because let's change this one slightly. So instead of 1, let's make another polynomial, and I'll draw it in blue. That's like y equals 5x cubed plus 2x. Let's get rid of the 1. Like the implications of, does that change the polynomial a lot? So that just shifts our polynomial, right? So our polynomial just moved up by 1. Okay, so let's draw it. But do we hit the secret point? We do not. So if we go to our friend and say, oh, here's another polynomial commitment, can you give us the secret point for that? Here's another polynomial, can you generate the secret point? They say, sure, I'll generate the secret point for you. They generate it here. And it's different. Like it's at the same x, but the y is different. Right? So our polynomial commitment is y. So this is, let's say this is just y1 and this is y2. So our polynomial commitment of y2 is different. So, yeah.
I have a question because the first equation you said +1, right? And now the second equation you -1. So is it supposed to be below?
No, there's just no 1. It's
No 1.
so yeah, it should probably be below, right? Yeah. It should. Okay. Yeah, you're right. Okay, so let's just call this one +2.
Okay, that's
+2.
that makes no sense.
Yeah.
Actually, it makes more sense.
Yeah, that makes more sense. And then we can do like +0, and we can move it down another one. Yeah. So like this is like the intuition here, is that like when you make polynomials, if you change a polynomial by a tiny bit, it changes the whole thing. Like these two polynomials, we change like 1 digit in the formula, and they're completely different. They don't share a single point. They're just wildly different. And that's like the other important thing to remember here, is that like when you change a polynomial, it just changes everything. Like once you change it a tiny bit, it just changes everything. And another thing to remember is that like it's really hard to make a polynomial that's similar to another. That's just like a hard mathematical problem, because this description is so short that like trying to find another description that's like equally as short, it's just really hard. Like finding another description that's equally as short and contains a lot of the same information, that's just a really hard problem. So like because of that, like those are two intuitions to why like polynomial commitments are hard to break. That like we're basically saying that like polynomial commitments are very delicate. Polynomials are very delicate. If you change them slightly, it just has huge implications on the rest of the polynomial. Cool. Any more questions?
So when you say polynomial commitment operates over a subset of the it operates over a subset of the what do you mean by that?
Okay.
Yeah.
So the definition of a polynomial commitment is that it's binding, so that like when you commit to a polynomial, you're not able to change the polynomial that you committed to. The other definition of a polynomial commitment is that, yeah. So what do I mean by that? So like that's what I mean, that like it's binding. That like there's no way for you to change the polynomial you've committed to after you've committed to it. And like there's many ways to make a polynomial commitment. Like another thing that we could do to make a polynomial commitment is we could just take the coefficients of the polynomial and just hash it all together. Like that's another polynomial commitment that kind of fits our scheme, but the problem with that is that it's hard to open our polynomial. That like we want, like when we say open our polynomial, we want to evaluate it at another point, and it's hard to do that. Okay. So again, this is not easy stuff. This is not easy. And we're almost done. Okay, so we've gotten to the point where we have like a polynomial commitment, and like the last thing that we need to do is we need to be able to open our polynomial commitment. And like, how can we do that? we can do that with this like subtract and divide trick here. So we start out with a polynomial that's evaluated at our secret. Maybe instead of doing this, maybe we should just talk about pairings and just have another. Well, let's just black box a pairing, and then we can finish. And like it can be homework to sort of see how you can open a polynomial commitment. So let's go through this last one. This is about an elliptic curve pairing. Right. So an elliptic curve pairing is kind of like an encrypted multiplication. So like we have our secret 1 and our secret 2 and we want to multiply them together. And like, yeah. We have our secret 1 and secret 2 and we want to multiply them together. So we're able to use like a pairing to do that. Pairing is a cryptographic operation that we can use to do this. So okay, so let's go through the code here. So you have secret 1 and we have secret 2. And basically we say, okay, let's first of all make 2 elliptic curve points. One of them, which has secret 1 encoded in it, and the other one that has secret 2 encoded in it. And then let's take the elliptic curve of point, the second elliptic curve, or the elliptic curve point, G2, and multiply it by the elliptic curve point, G1. We multiply them together, and we get this result. And then we just switch the order. Oh, that's G2. Oh, that should be G1 times G2. So, sorry, this should be G1, and this should be G2. Oh, no. Oh, so, oh, wait, am I doing that here? Oh, yeah, okay. Okay. So, like, basically what I'm doing is that, like, in the first time I calculate G1, I do G1 multiplied by secret 1. The second time I calculate G1, I do G1 multiplied by secret 2. I just switch the order of them. And basically what I'm doing is I'm kind of saying that, like, so this is more secret stuff, right? So I say G1 times secret 1 times S1. And then I say G1 times S2. And I say G2 times S2, G2 times S1. I do a pairing of both of these things. I do a pairing of this, and I do a pairing of this. Right? And then it turns out that like these two things end up being equal. Right? So this is a very important tool for us because it means that we're able to like do equality checks between different things. Right? If we have like, it means that we're able to have like 2 secrets that can cancel each other out. And that's a key thing that we use to open our polynomial commitments. Okay, so let's start to slow down now. We're almost done. This is very difficult stuff. This is very difficult stuff, and yeah, this is very difficult. Yes. Okay, let's do it. Visuals are always good. Okay. Sorry? Hey, let's try. Okay, so let's try to do something like this. So, like maybe we can talk about our friend again and just say that like, oh, we have someone who's doing this for us, just so we can see what's actually happening underneath. And then we can talk about the actual insights. Okay. Okay, let's see. Okay. So let's take G1S1 and say that it's here. G2S2, let's say it's here. G1S1, let's say it's here. And G2S1, let's say it's here. Okay, so this is G1S1. This is G2S2. This is G1S2. This is G2S1. Okay, so like the point is that these two things are equal. When we do this operation, it turns out to be equal. So there's this symmetry here where it doesn't matter. You can flip which one G1 is on, or S1 and S2. You can switch them around and it still results in the same thing. So how can we visualize that? So what kind of transformation can we use to represent the pairing? So I guess the transformation is going to be something like it goes to the same point. Yeah, okay. Okay. So this is what happens. Like when these two go together, they end up at the same point. So visuals are definitely good. I should go through the tutorial again and try to come up with like more visual descriptions. Right. But like we can definitely come up with something that like makes sense here. I just need to change the locations of these things that like G1S1, G2S2. Right, so let's just do it with like additions. Let's just say we add these 2 points together. And then we just need to be clever about exactly where we put the points. But like, there's something hard here about like there's something really difficult here because like conceptually it's really hard to have this kind of thing. But like, I guess we can take something else that is similar, that's like homomorphic, which is just like multiplication, I suppose. But like, yeah, okay. Right. Okay, so let's do that. Let's say that these are just actual multiplications. So, sorry? So let's say that we have G1S1 is just a product of two things. And then let's say that like G2S2 is a product of something else. And when we do the pairing, we just multiply these two things together. So that's this point here, that's this point here, and we multiply them together. How will that? Yeah, so this is a number line. Okay, so this is not 2 dimensions, this is 1 dimension. Okay, so when we multiply these two together, we'll end up with a point over here, which is just like these two goes to here, right? Okay, and let's look at the other option, which is G2S1. So G2S1 will be here. G2S1 will be here. G1S2 will be here. And basically, when we multiply them together, we'll end up at the same point, right? Because we're basically multiplying the same things together, right? So that's like a more, like, you see what's happening here? That like these two, but these should be different though, right? Yeah, because like the product is different, but it's like, right. So okay, so let's take an example of this and see if it actually works out. See if my understanding is correct. So let's go back to the integers. Like G1 and G2 are actually elliptic curve points. Well, let's just go back to the integers and see if we can have an example of this that makes sense. So let's say that G1 equals 2 equals 2 and G2 equals 4. Okay, and then let's say that S1 equals 2 and S2 equals 4. So let's actually calculate these things out. Let's say that the operation here is multiplications. Oh, the operations here is multiplications. So that's let's replace the pairing with multiplication and see if this actually works. Okay, so G1 times S1 should be 4 multiplied by G2 times S2. G2 times S2 is 16. So 4 times 16 is what? 32, 64. Okay, and then let's take the second one. Let's say, what was the first one? G1, S1. Okay, so let's take G2 times S1. So 4 times 2 multiplied by 4 times 2. 4 times 2. So that's 8 times 8, which is 64. Okay. So that's like a more, that's like, it's the same deal. You know, it's just like multiplication. Pairing operations are homomorphic, and so is multiplications. It doesn't matter what order the secret is in, you're going to end up at the same place. So like the cool thing that a pairing lets you do is that it lets you keep the secrets. That's the key intuition here. Because when we do this, multiply, we lose secret 2. We don't know what secret 2 is anymore. And it's impossible to go back. That's the key that's the key learning about elliptic curves. Elliptic curves let you go forward with multiplication, but you can never go back with division. It's only one direction. So because of that, pairings allow us to do this encrypted multiplication. It's like this homomorphic operation that we're eventually able to use to do our opening. Because like one of the tricky things that come up when we talk about pairings, when we talk about elliptic curves, or when we talk about polynomial commitments, is how can we open the polynomial commitment at another point? And the way that we do that is we use a pairing. Because we have two representations of the secret, we're able to use the homomorphic nature of a pairing to open the polynomial commitment at another point. We can kind of cancel out the secrets. Okay. I'm so sorry. That is very difficult stuff. Very difficult stuff. This is like the key. This is the basis of like the Plonk ZKP. Like understanding these primitives are. That's what you need to understand in order to understand like all of the ZKP. But like you don't need to worry about like understanding everything in order to be able to build things, and you don't need to worry about understanding everything in order to be able to like improve and optimize and make better proof systems. You can focus on FFT or other parts of the whole picture. You don't need to understand everything. For example, understanding like the intricacies of how the pairing actually works. Like so far, we talked about what the pairing does, but like understanding how a pairing works is super complicated. It's really involves a whole bunch of math and a whole bunch of difficult things to try and understand. So I think we're gonna finish up here. Do people have questions? I'm sorry for like we sort of went from like kind of easy stuff to like super complicated stuff to like very, very complicated stuff with very little kind of like transitions. But questions?
So what is the key difference? What is the key difference between Plonk and prosody?
So like the key difference is that like so there's a couple of different interesting things. So the surface level thing is that Plonk has a universal trusted setup. So you don't have to do a trusted setup for every circuit. You can just do like a single trusted setup. Like we kind of talked about that when we talked about the powers of tau. That's one big difference. But the more nuanced explanation is that Plonk allows you to do like two really cool things. First of all, it allows you to do custom constraints. So we kind of alluded to this earlier when we were talking about like our polynomial that defines our constraints. We talked about like being able to do multiplications and additions, but it turns out that we're able to do like much more complicated constraints, that we can do like multiplications and additions, and we can do like cubing and things like that. We're able to have more complicated constraints. The other really, like a second really interesting thing is that it allows you to do lookup arguments, to use lookup arguments, which is basically like a set proof. And that's really efficient way to do range checks and to make things like the ZKVM possible. Lookup arguments are important for that. The third thing that it lets you do is that like, because the polynomial commitments are separated, and because it's just like, because it's separated, you're able to like aggregate together many polynomial commitments. And you're able to make these really cheap aggregations of proofs, which is really interesting for a whole bunch of other applications. Like, for example, we have a quadratic voting ZKP called Macy, and Macy needs to put ZKPs on chain to verify the result of the vote. And when you put them on chain, you need to verify each proof. But we do this on optimistic rollup, so it's a bit cheaper. But like, we still have to pay the call data, as we talked about yesterday. Call data is the only thing that's expensive on layer 2. It's the only thing you have to optimize for. And ZKP call data is impossible to compress. So that becomes really, really expensive. So we want to use proof aggregation to compress those proofs into like a single proof on chain, so that we're able to reduce our gas costs further. So like, those are, for me, the killer features of Plonk. I think the major killer feature is aggregation, being able to merge multiple proofs together. It's really, really important. It helps you for scaling, but it also helps you for like building more interesting things like the ZKVM. We need to have aggregation in order to be able to have like dynamic circuits and adjust the way our circuits laid out.
So can we do recursive proof?
So I think I'm not really sure on the difference between aggregation and recursion. I think that like aggregation means that like you don't ever finish verifying a proof until you verify all the proofs. I think recursion means that like one proof verifies a whole other proof. But so let me just repeat the question just to make sure. Like, the question was, can you do proof aggregation? Or can you do recursion? Because we all already talked about doing aggregation. So I think it's definitely possible to do proof recursion, but it's probably not as efficient because you need to do a pairing check inside the ZKP. And like, that's going to be crazy expensive because like, not only is the pairing very complicated to understand, it's also complicated to verify. Yeah. Does that answer your question?
Do you know any transparent polynomial commitment scheme?
Yes, Fry. Fry is a transparent polynomial commitment scheme. They're the basis of Starks. Starks use Fry. Fry, F-O-R-I, yeah. So like, this is an important thing to mention, that like, what we talked about today is like Plonk arithmetization and the KZG polynomial commitment scheme. And together they're known as Plonk, although that's really confusing. I wish we could separate the polynomial commitment scheme from the arithmetization, because like, they're two separate things. For example, you could take all of the arithmetization we talked about earlier and combine that with Fry, and that would be like, that would totally work. Like, also, when I say arithmetization, I mean that's how you lay out your circuit. That's the tools. That's multiplications and additions. It's the tools that you have to define your circuit.
So why don't we use Fry to in place of this polynomial commitment scheme to remove the trusted setup phrase?
Yeah, we can do that. The major thing that it will cost is that the verification cost will be higher. You'll have to verify the Fry polynomial commitment scheme instead of KZG. But that should be fine because we can use proof aggregation, or with Fry, we can even do recursion. And we could use that, although aggregation and recursion are, I don't know if there's a real benefit to doing one over the other, but anyway, that's, yeah. I think that like, we could, yeah, with Fry, we could even do that. So like, that's an interesting project for sure. You could take like the Halo 2 proof system or proofs library that doesn't use a Halo 2 polynomial commitment scheme and replace it with Fry. And then you could use like the Halo 2 library to define your instrumentization, and you can use your Fry proofs to verify the proofs on chain. And yeah, that would work, and that would be really cool. That sounds like a great project.
Thank you.
Yeah, sure. Cool. Any other questions?
I have a question. Is G1 and G2 in the same elliptic curve generated point from the same elliptic curve?
So is G1 and G2 generator points from the same elliptic curve? I think that they're two separate elliptic curves. And like the pairing kind of like moved from those two elliptic curves to a third elliptic curve. It's called GT. Yeah. Cool. Okay. Thanks, folks. Let's have a lunch. Good job today.
Okay, so thank you everyone for joining the second workshop. Let's grab up. And then like, if you want to rewatch the workshop today, you can go to, again, our ETH Vietnam Facebook or YouTube, or even Dora Hacks also have the video. And then also, we also send you through the email that you register. So hope that you also have the time to revise all the knowledge, what you have learned today. Thank you, everyone. And then keep in touch, and please join our ETH Vietnam community to have more update about the next coming workshop also. So tomorrow, Barry also like do a workshop in Hanoi. Also like to continue the workshop chains about ZKP. And what else, Barry?
Quadratic funding, bribe resistant mechanisms.
Yeah. So we also gonna do the live stream on our page. So if you want to continue the workshop in Hanoi, actually it's not the same like this, it's continuous. So like you also can join on through live stream on our page also. Yeah. Okay, thank you everyone. And let's have lunch. Yeah.
Questions to ask. So,
Oh, yeah?
do we have any communication channel?
Yes, we have the Discord channel. The link can show the QR code also, and also they have the information with Barry. Also, I can, if you have, session with Barry also.
Yeah.
Buổi tối có đeo lên. Không có hả? Okay, let us share the Discord channel via email. Okay, and also Barry.